Okay. Hello guys. Today we start a new topic, which is inductance. And in particular, this lecture we will consider such effect as self-induction. So far we were considering only induced current and electromotive force by changing external magnetic field in some which was causing some change in magnetic field flux through some current loops located in this external magnetic field. However, it is also possible to change magnetic field flux through like some closed loop, current loop, which is electric circuit, when this magnetic field flux is created by magnetic field generated by electric current flowing through this closed loop. That effect is called self-induction, and we will try to first discuss the general concepts of this effect, and also a bit later give quantitative description of self-induction effect, while we also consider some resistance inductor electric circuits. So it will be RL circuits. Okay, so let us switch to the slides, and let us consider electric circuit, which consists of a resistor, a battery, and a switch, which can turn on and off the electric circuit. Here is our switch. Then we have a resistor. And here is a battery. So resistor R minus epsilon. This is our electromotive force of the battery. So the direction of current is counterclockwise. And when we turn on this switch, we definitely have some current flowing through the circuit, and this current generates magnetic field. So this is how we will show direction of magnetic field lines around this conductor. So let us consider initially not working electric circuit. So when this switch S is not connected, then nothing is going on. There is no current, no magnetic field. However, at some time t equals 0, we turn on the switch, and electric current starts to increase. So we would say that it's known the magnitude of electric current for this simple electric circuit, and it would be equal to electromotive force of our battery divided by resistance, assuming that we don't have any resistance of connecting wires. However, so this is true. However, this current will not reach immediately, instantaneously, this value. So it will increase with some rate, but it will be time-dependent process. So it will increase from 0 and finally reach this saturated value defined by epsilon divided by R, but there will be some time dependence. And our goal is to understand the origin of this time dependence, like the physics behind it, and also describe it a little bit later quantitatively. So in other words, our goal to understand the effect of self-induction during this lecture. So we know that current increases. So if current increases, then the magnetic field flux originated from this current also increases. So we have some rate of changing magnetic field flux through a closed conductive loop. So obviously there will be induced some electromotive force and some induced current in this loop. And according to Lenz's law, the direction of this induced current or induced electromotive force is such that the induced current in the loop will establish magnetic field opposing the change in the original magnetic field. So it means that the direction of the induced electromotive force will be opposite to the electromotive force of the battery. Here we need to distinguish quite clearly between some physical electromotive, let's say electromotive force generated by batteries, and electromotive force which is induced by changing magnetic field flux. So this induced electromotive force originated by changing the magnetic field flux due to changing electric current in this circuit will be directed opposite to the electromotive force of the battery while we turn on this circuit. If we reach the saturation, our current goes up to this value, maximum value epsilon divided by R, and then we turn off the circuit. Then it will be in the contrary, because in this case, our current will start to decrease. And again, it will not decrease instantaneously. It should be some, let's say if we eliminate this battery from the circuit, then our current will not decrease instantaneously. We will see some decay over time. And that is because the electromotive force which is induced in this circuit will oppose the reduction of electric current, and that's why there will not be observed instantaneous reduction of current in the circuit. So we can write the expression for the induced electromotive force. Let's call it epsilon L. And according to Faraday's induction law and Lenz's law, we have such an expression, which we already know, that it's proportional to, like equal to negative of the rate of changing of magnetic field through this loop defined by the electric circuit. And this could be also written as minus L times di over dt. So here we see that induced electromotive force is proportional to the rate of changing electric current through the electric circuit, and the proportionality coefficient L is called inductance. So inductance is a parameter. So this constant for given electric circuit is a constant, and this constant is determined by the geometry of electric wires and also some other characteristics of the environment. We will discuss it later. Let's say if we have some closely spaced coil with n turns, some ideal solenoid, then this induced electromotive force can be expressed as minus n times dB over dt, as we discussed earlier. So n is the number of turns in this coil. Then we can proceed further and say, okay, this is also equal to minus L di over dt, the rate of changing current in this solenoid. So from here, since we have dt and dt in the denominator from the left and right side, we can write the inductance of such a solenoid would be equal to N magnetic field flux over I. So this is the particular case when we deal with solenoid. And in other form, inductance can be written also as minus epsilon L divided by the rate of changing the current, di over dt. So if we compare this last equation with definition of electrical resistance, with delta V over I. So we can call electrical resistance as the opposition to electric current. And in that terms, we can also call inductance as the opposition to the change of electric current over time, because here in the denominator we have electric current and here change of electric current. So there is a special unit which is used to quantify inductance in the international system of units, and that is Henry. So Henry, H. So 1 Henry is equal to 1 volt second per ampere. So these are units, and as I mentioned earlier, inductance is similar to capacitance, depends on the geometry of conductors. And that is the main factor which determines inductance of different electric circuits. Any conductor possesses some inductance, but depends on the geometry. Some could be very small, like straight wire, or some can be quite large when we have a coil with many turns, like some solenoid or toroid. So let us consider an example of some uniformly wound solenoid having n turns and length L. So we have n turns and the length of the solenoid is L. We also consider that L is much larger than the radius of this solenoid, and it's filled with air. So there is no some ferromagnetic material inside the solenoid. So magnetic field flux is equal to the product of magnetic field times area of the solenoid, assuming that we have this ideal solenoid and uniform magnetic field in the interior region of the solenoid. Then it's equal to mu naught times n times I times A. So n is number of turns per unit length, so we can write it in a different form, n over L times I A. And assuming our equation from previous slide for inductance of a solenoid, which is n times magnetic field flux divided by electric current, we will get expression for the inductance of the solenoid in terms of mu naught times n squared over L times area. So here, if we assume that this total number of turns in the solenoid is number of turns per unit length times the length of the solenoid, then we substitute it in this final equation here. We will get L as equal to mu naught times n squared times L squared divided by L times A. And here is mu naught times n squared times AL. And this AL, so this is area cross section of the solenoid, and this is length of solenoid. So this is the volume defined by solenoid, so interior volume of the solenoid. So we can write that here it will be mu naught times n squared times volume of the solenoid. So this is a example of calculating the inductance of a solenoid. It could be quite challenging to calculate inductance of conductors of some complicated shapes. However, when they have some symmetry, that is possible to do in a relatively simple way. So now we want to, so we mentioned several times already about time dependence of electric current when we turn on and off the circuits. That definitely is a very important feature, which we need to describe quantitatively. So I mean, we need to get time dependence of electric current in the presence of electromotive force, resistance, and some inductor. So let us probably first introduce what is inductor, and then proceed further with so-called RL circuits. So if an electric circuit contains a coil, such as solenoid, the inductance of this coil prevent the instantaneous increase, like instantaneous change of electric current in the circuit. That is happening because of this mentioned self-inductance effect. And also each of the element of electric circuit, each conductor, as I mentioned before, possess certain inductance. It is convenient to concentrate all inductance of electric circuit in one element of this electric circuit. And this element is called inductor, and it's shown as some coil on electric circuit. So if we see such inductor in electric circuit, we assume that all inductance of the electric circuit is concentrated in this single element called inductance, and usually marked with this capital L. Sorry, so called inductor, and this inductor possesses its feature, its inductance, which is measured in Henry. So now let us consider electric circuit, which will contain two switches, one battery, one resistor, and one inductor. So this will look like this. We have our electromotive force of this battery. Here's plus, minus. Here's the switch, S1. Here is the switch S2. And two positions of the switch A and B. Then we have a resistor. Our inductor. L. And the condition here is that switch S2 should be always in the position A or in position B, so it cannot be in some other positions. So it always connected to either point A or point B. So let us consider, model the situation when switch S2, S1 and S2 are turned on. So S1 is just turned on and S2 is turned on in position A at T equals 0. So we have this position of S2 in when it connected to point A. Here is our resistance R. So in this case, there will be some current flowing through the circuit. Show it I. And since we have this inductor, this current will not change instantaneously to its maximum value. So saturation value of current is epsilon divided by R, because we assume that inductor doesn't have any electrical resistance besides inductance. However, it will not reach instantaneously this saturated value because of the self-inductance effect. So what will happen here? When we go from electric current equals to 0 at time equal to 0, the moment when we turn on the switches, electric current will increase, magnetic field flux will increase. That will generate some induced electromotive force, which will be kind of originated within this inductor, since this all inductance of the electric circuit is concentrated here. And there will be some polarity of electromotive force in opposite direction to the polarity of electromotive force of the battery. So induced electromotive force will be in opposite direction as the electromotive force of the battery, which causes the increase of electric current in this circuit when we turn on these switches. So in this case, we can write the Kirchhoff's equation for this circuit when we traversing this circuit in the clockwise direction. It will look like this. So we have some electromotive force of the battery and minus voltage drop over the resistor and minus this induced electromotive force, which will be equal to L times di over dt. And this is equal to 0. So now we have a differential equation, which already the solution of which will provide us the information on how electric current will change in this circuit with time. So in order to make the solution of this differential equation easier, we should proceed with some substitution of variables in order to make it more convenient. So we will consider x equal to epsilon divided by r minus I, and dx will be minus I. So with this substitution, we can rewrite the differential equation. It will be x plus L over R times dx over dt. So this is equal to 0. And now our task is to rearrange this equation and integrate it. So let us go to another slide. And again, let's write this equation, x plus L over R dx over dt. And so this is equal to 0. So after rearrangement, we can have dx over x is equal to minus R over L times dt. Okay, now we need to integrate this. Integral from x0 to x dx over x is equal to minus R over L integral from 0 to t dt. So we will get the integral after integration will be natural logarithm of x over x naught equals to minus R over L times t. And x naught here is the value of x at t equals to 0. So after getting rid of natural logarithm, we can go to the exponential function and express our x as x naught times e in the power of minus r over L t. So at t equals 0, we know that electric current is equal to 0 because the switches were open and they are closed only at t equals 0. So initially current was equal to 0. That means that based on the definition of x, which we gave for on the previous slide, we can write that x naught is equal to epsilon over r. Now we can substitute expression for x naught here and for x here. Let us do it on the next slide. It will be epsilon divided by r minus I equals to epsilon divided by r times, sorry, it's too early here, times e in the power of minus r over L times t. So when we rearrange this and express our electric current as a function of time, we will get the following. So it will be current as a function of time will be equal to epsilon divided by r times 1 minus e in the power of r divided by L times t. Okay, so this is the expression of the time dependence of our electric current, and we see that it changes not instantaneously from 0 to epsilon divided by r, but follows some exponential dependence. And what is interesting, that if we assume some electric circuit with 0 inductance, so we don't have inductor in our electric circuit, then exponent becomes equal to 0. So electric current will not depend on time anymore, and it will increase instantaneously to its maximum saturated value, epsilon divided by r. However, this is not true because in real electric circuits, inductance is not equal to 0 under any circumstances. It could be very small, but still not equal to 0. So another option to modify this equation, which we derive, is to introduce this time constant, RL time constant, tau. So tau time constant is equal to L divided by R. And then we can write in the final form this current time dependence as epsilon divided by R times unity minus E in the power of minus T over tau. So this is the final expression, and we can show graphically how this current will change in the considered electric circuit with time. Here is time t, here is current I. So we can show that it will change something like this. So here is some saturated value up to which this current tends to increase. And of course, this is epsilon over R value, saturated value. And at some t approaches to infinity, this current value will reach the maximum saturated value, which is epsilon divided by R. So another thing which is interesting to consider is the rate of change of the current. So that is derivative of this function which we derived for I. So it's di over dt. And that will be equal to minus epsilon over R times e in the power of minus t t over tau. And that also we need to multiply by the derivative of the argument of the exponential function, which will be 1 over tau. And eventually we will get this equation, epsilon over R times e in the power of minus t tau over tau. So we see that the rate of changing current is maximum at t equals 0. And then it exponentially decreases while the electric current approaches to closer and closer to its saturated value. That is quite clear because if we have smaller change in electric current magnitude, then we will have smaller induced electromotive force at the inductor, and that will in smaller extent oppose the change of electric current. So we will see some smoother and smoother approach of electric current to its saturated value, defined by the electromotive force of the battery and resistance of the electric circuit. So now let us consider that we waited long enough to reach this saturation. So we got some constant electric current in the circuit, which is equal to epsilon divided by R. And then we do some manipulations with our switch S2. So we, let's go back and look again at our electric circuit. So we switch from position A to position B. That switch happens instantaneously. And if we do that, we eliminate electric battery from the circuit. So we have circuit which is defined only by resistor and inductor. Okay, and then obviously we will have some attenuation of current. It will decrease, but it will not decrease instantaneously because of self-induction effect. There will be some self-induced electromotive force at the component of our electric circuit called inductor. So let us discuss this question quantitatively. Since we eliminated the battery, there is no electromotive force in the equation of like Kirchhoff's equation for this new electric loop. And we can rewrite it as voltage drop over resistor plus induced electromotive force at the inductor will be L times di over dt. And this is equal to 0. So we can rearrange this in order to have the final form of differential equation before integration. So that could be written as I times R is equal to minus L di over dt. And from here, we can write that di over I is equal to minus R over L times dt. So now we need to integrate this. And we will get natural logarithm of electric current is equal to minus R over L times T plus some constant. So we need to determine this constant from some boundary condition. And boundary condition, we know that at T equals 0, in the moment when we switch to this switch S2 to the position B, our electric current is the maximum, possess maximum magnitude in this electric circuit, which is equal to epsilon electromotive force of the battery divided by R. As we mentioned earlier, we were waiting enough long to let electric current in the circuit to reach its saturated maximum value. So again, at this time equals 0, at the moment of switching S2 in the position B, the current in the circuit was equal to epsilon divided by R. And that means that so we should substitute instead of electric current its value here, natural logarithm of epsilon divided by R is equal. So here this term will be equal to 0 because T is equal to 0, and this will be equal to C. So our constant is equal natural logarithm of epsilon divided by R. Now we can substitute expression for the constant in our equation here. So it will rearrange it. So we can, it will be natural logarithm of I minus natural logarithm of epsilon divided by R. And this will be equal to minus R over L times T. Or taking into account the feature of our logarithms, we can write natural logarithm of I over epsilon divided by R is equal to minus R over L times T. Now we get rid of natural logarithm by using the exponential function, and that will be I over epsilon divided by R equal to exponent of minus R divided by L times T. From here, we get the final expression for electric current as a function of time in the decaying mode when we eliminate the electromotive force of the battery, like eliminate the battery from the electric circuit by switching S2 to position B in our electric circuit. So that will be I as a function of time equals to epsilon R times exponent of minus R divided by L times T. And this will be our initial current, And we can also use time constant. So the final expression will be I as a function of t equals I initial exponent of minus t over tau, which is tau, it's RL time constant of the circuit. Tau is equal to L divided by R, and initial current is this maximum current in the circuit, epsilon divided by R. So if we set L equal to 0, then electric current would instantaneously drop from its value epsilon divided by R to 0. But this is not the case in reality, and that's why we don't observe instantaneous reduction of current. It changes, like reduces over time by exponential function of time. And that will be graphically represented something like this. So here we have current, here we have time, and it goes from initial maximum value, which is epsilon over R, and exponentially decays to 0 at after sufficiently long time interval when t approaches infinity. Of course, it is it's all defined by the time constant of this electric circuit, but at this condition of time approaches infinity, doesn't matter what is time constant, all induced, for all electric circuits, this current will reach its minimum value, which is equal to 0. Okay, that's pretty much everything I wanted to tell you during this lecture. We will continue further with considering mutual inductance effect, when we have effect of like some self-induction in the system of coupled solenoids or electric wires. We'll also consider in more details later electric circuits which possess not only resistors and inductors, but also capacitors. That will be RCL circuits. But that will be during our next lectures. So thank you very much for attention. Take care and have a good evening. Bye-bye.